Hello, my name is Noor Jallad. I am 19 years old. I am Palestinian. I am a student of computer system engineering at Palestine Technical University Khadouri. First, I would like to say, when we think about developing technology that brings comfort to humans, such as making cars, we should think about something more important, which is to maintain human safety from this technology, such as thinking about things that reduce disasters resulting from cars, such as accidents. The paper ID is 157-067-6404. The paper name is Graph Representation for VANETs based on HashMap of ArrayList and pairs. Dr. Yusuf, who is my research partner, has been supportive of me in every step. I thank you very much. Introduction. Vehicular ad hoc networks, VANETs, consist of vehicles communicating with each other. VANETs can be used for safety applications and traffic control applications. Computations have to be based on fast algorithms with low computation time complexity. VANETs utilize a graph to represent the vehicular structure. Each vehicle is represented by a vertex in the graph, and the communication with another vehicle is represented by an edge. A problem. Graphs are usually represented by adjacency matrix or by adjacency list. But these methods have several disadvantages that affect VANET communication efficiency. The first problem, the adjacency matrix representation dominates most of the proposed VANET algorithms, consumes much computation time, which may seem small, but because of the large number of vehicles, this time can be summed up to a significant amount. The second problem, the adjacency list representation method, is not widely used in VANET, but this method also consumes much time when the graph is big and dense. Solution. The proposed algorithms utilize the well-known representation methods, such as adjacency matrix and adjacency list. To achieve more efficient communication, this paper proposes a method to represent a graph based on HashMap of ArrayList and pairs. In this method, a map should a length equal to the number of vertices. The first field in the map contains a key, which is the vertex name, and the second field contains an array list of pairs. Each pair contains a string value to store the adjacent vertex name, and a numerical value to store the weight on the edge. In this way, all vertices are mapped to their adjacent ones by an array list, which has lower time complexity than adjacency matrix and adjacency list for basic operations such as insert, delete, access, and search. Material and methods. Effect of computation time on VANET. The idea behind the proposed method is reducing the computational time required by each vehicle for performing computation on VANET graph. The computation time can dramatically grow up because in VANETs the number of vehicles participating in the routing is large. When computation time is large, a delay will be caused and the message may not reach the destination at the required time. Reducing computation time. The speed of the graph algorithms depends on the representation method of the graph topology. As we explained in the previous slides, that the adjacency matrix method and adjacency list consumes much time and memory. The proposed graph representation method can be represented by the following. And figure 1, it is example of a graph of 5 vertices and weight on edge. The representation for the graph can be represented by the following. The representation guarantees that each vertex is associated with its adjacent ones in the graph, and the weight is also represented without adding new burdens on the storage resources. This representation also allows for dynamic topology when the structure of the graph is dynamic, and vertices need to be added and deleted continuously. Experiments and results. Strongly connected components results. The strongly connected components is necessary for forming connected set of vehicle we tested the proposed method to find the time required for forming a strongly connected component in Scenario 1 and Scenario 2. Table 1, it is the time in milliseconds required to form strongly connected component for Scenario 1. And the Table 2, it is the time in milliseconds required to form strongly connected component for Scenario 2. We note from the values in the two tables, the proposed method is better than the adjacency list and adjacency matrix method. The time for the adjacency matrix, which is popular in VANETs, is larger than the others. And although the adjacency list performs well in Scenario 1 when the number of vertices is small, its performance deteriorates in the second scenario. In fact, the second scenario is more realistic because in VANETs, each vehicle is usually allowed to communicate in both directions. The adjacency list method consumes much time in the get method, which used to find the adjacent vertices. This time is linear and can be expressed as O of n. Meanwhile, in our method, the adjacent vertices can be found in constant time. A breadth-first search results. The breadth-first search algorithm is necessary in graphs for finding the shortest path when the weight on edges are equal, which is valid for some assumption in VANETs. We tested the proposed method to find the time required for forming breadth-first search in Figure 4, in this figure. Table 3, it is comparison between the method for breadth-first search, the time in milliseconds. Table 3 shows that the proposed method outperforms the other methods as it consumes less time for discovering the graph by the breadth-first search algorithm. The other significant result is that the proposed method still performs well when the number of vertices is large, while other methods could not produce results because of the out-of-memory error. This error is caused by the high computational space demand. Depth-first search results. The depth-first search algorithm is necessary in VANETs for finding the connected dominating sets for reliable and efficient routing. We tested the proposed method to find the time required for forming depth-first search in Figure 4, in this figure. Table 4, it is comparison between the method for depth-first search, the time in milliseconds. It is clear from Table 4 that the proposed method outperforms the other method because its running time for computing the depth-first search algorithm is less than the others. The proposed method even produces results when the number of vertices is large, which is very common in VANETs. The reason of the low computation time is that the proposed method depends on the HashMap and ArrayList structure, which required constant time for the basic operations such as insert, search, and delete all axes. Conclusion, the computation time of graph algorithms in VANETs increases the total transmission time and the delay of messages. First, in fact, most proposed algorithms of VANETs depend on adjacency matrix graph representation, which consume much computational time and memory. This paper proposes graph representation method that depends on the HashMap of ArrayList and breadth data structure. This method is applicable in VANETs where graph is widely used to represent vehicles in the graph topology. Secondly, the proposed method reduces the computational time as it requires constant time for the basic operations such as insert, search, access, and delete. Finally, the proposed method was tested in different scenarios and compared with the adjacency matrix and adjacency list. The results show that the proposed method outperforms the other methods as it produces results for the strongly connected component breadth first search and depth first search in smaller than the others. Our future work will focus on developing an efficient VANETs routing algorithm that utilizes the proposed method. I hope you like my idea and thank you very much.